Now we will see how the substituents affect the acidic strength. Effect of substituents on acidic strength. Effect of substituents on acidic strength of phenols. Okay, if in phenols, what if there is a substituent present? What if there is substituent present? Substituents with some other group. We'll take two conditions. If it is electron withdrawing group, electron withdrawing group, so I'll write it as EWG. Okay, electron withdrawing group if it is present. Electron withdrawing group like nitro, cyano, etc. Which can pull the electron towards itself. What if such groups are present? What may happen? Now say in the place of X it is nitro or CN, any group. It is electron withdrawing group. That means it pulls the electron towards itself. It pulls the electron towards itself from oxygen. So it forces this oxygen. See, you have lone pair of electrons. So you have to give the electrons to me. That means it will try to donate the electron towards itself. So it pulls the electrons. If it pulls the electron, what happens to oxygen? Oxygen becomes, if that case happens, then oxygen becomes positively charged. Then this will acquire more electrons if the electrons are pulled. Are you getting the point? If it is electron withdrawing group. Withdrawing means the one which pulls the electron towards itself. Then what happens? Here oxygen becomes positive. Now what happens to hydrogen? Hydrogen will think, see, I got bonded with oxygen because it was negative, electronegative. Now it has acquired a positive charge. So it will start thinking. So it will plan to break the bond. So what happens? Can it donate H plus or not? It can easily donate H plus ion, isn't it? It can easily donate H plus ion. So what happens? This can become O minus with X plus H plus. It can donate H plus ion. Therefore, what happens to acidic strength? Acidic strength increases. Same way, let us see if suppose this was a case for electron withdrawing group. If it is a case for electron donating group. So you have phenols now. And there is say some group attached, say X or X, which is electron donating group. Now it is electron donating group. Electron donating group can be CH3, methyl group is electron donating, Cl, F, or amine group. These are all electron donating groups. If those electron donating groups are present, what it will feel? It will be like, oh, already oxygen will be having two lone pair of electrons. So this X will start donating electron towards oxygen. So what happens? Oxygen becomes more and more negative. Now what happens? This becomes more and more negative. Will the hydrogen bond break now? In this case, so hydrogen will be like hydrogen. See, now the case is like this. OH bond means this is more and more negative. It pulls the electron from this because it is electron donating, very generous, it gives electron. This is positive. Now there is more difference, isn't it? If there is more difference, they can bond even better. So hydrogen will not easily leave. That is why in the presence of electron donating group, the acidity decreases. What happens? Acidic strength decreases. Make a note of it. It is effect of substituents. The group present apart from OH group. Along with OH group, when other groups are present, if it is electron withdrawing, then what is the condition? Acidic strength increases. If it is electron donating group, then acidic strength decreases. Now let us see next reactions. That is properties of phenols. One more property is esterification. One more property is esterification. Esterification. What is esterification? Esterification is the ability to form esters, the formation of esters. Esterification, formation of esters. So what forms esters? Now phenol, esterification is the process where phenols can react with acid chlorides or carboxylic acids or acetic anhydride, or say acid anhydrides. What happens when they react? To form esters. This process is called esterification. Easy, right? Phenols react with acid chlorides or carboxylic acids or acid anhydrides to form esters. Now let us see the reaction, how the reaction goes. Okay, it's very, very, very easy and interesting also. We'll say carboxylic acid. Phenol reacts with carboxylic acid. Say I'll take it as R-COOH. In the textbook, for the simplification sake, I have written OH phenol group this way, or phenol structure this way. In your textbook, instead of this, they have mentioned it as AROH. That means to the aromatic ring OH is attached. This also it can be given, so it is given as R-. I'll write the same way. So what happens? This takes place in the presence of any acid. It requires some acidic medium. I'll tell you why it requires some acidic medium. Now here I will tell you what is the formula for esters. Okay, ROCOR-. This is the formula for esters. Instead of R, we have AR here, aromatic ring we have. So to the aromatic ring, which group must be attached? OCOR- group attaches. Here where do we have? This O remains as it is, okay? This O, this R- comes and attaches here. And what is the remaining things you have? What can be the byproduct here? H plus OH forms what? H2O. So the products are to the benzene ring. O already it is there. Here this CO attaches to O and then R-. OCOR-. What is it? It is ester. Now esterification has taken place. What is the byproduct formed here? Byproduct formed is H plus OH. H2O. Why this acidic medium is? Acidic medium helps for the formation of water. That if water forms, then there's nothing to disturb this one, ester. That is why it balances, neutralizes. Esterification. Esterification is a process where phenol reacts with carboxylic acid to form ester, or the other two condition also we are going to write now. It's clear? Or otherwise, how you can write this? Phenol plus carboxylic acid in the presence of acid ArOCOR dash plus H2O. This is how in the textbook it is mentioned. Along with alcohols it is mentioned. So hope this will be clear if you understand. Next is for acid chloride. Acid chloride. Acid, you know, no? The general representation is COOH. Acid chloride is in this, apart from OH, we have Cl. Our COOH is acid. Acid chloride means that OH will be replaced by Cl. So acid RCOCl, acid chloride. Let me mention, this is carboxylic acid, this is acid chloride. They call it as acetyl chloride also. Acid chloride. Now what happens? Now here the condition is this takes place in the presence of pyridine. Pyridine is a base. Pyridine is a base. Now here again what has to form? We know the formula for esters. What is the formula for ester? To the aromatic ring OCOR dash should be attached. OCOR dash will be attached. So it becomes benzene ring OCOR dash plus. What is the byproduct now? What is the byproduct? Here H plus Cl minus forms HCl. Now what is this formed? Formed is ester. Clear? Let's move on to the next reaction now. Next reaction is where acid anhydride reacts. Acid anhydride. Okay. See, anhydride means it is like this. They write it this way. RCO twice O. This is the formula for acid anhydrides. Okay. I'll try to simplify the structure. It is RCO with one oxygen bond this way. That is why we write RCO twice O. Acid anhydride. So let us see how the reaction takes place. OH phenol plus, again, how do you write acid anhydride, or it is also called acetyl anhydride? RCO twice O. In the presence of again acidic medium. Why acidic medium? Because here why we have taken base, you know, pyridine is a base. Why we have taken base is during the formation of ester, the byproduct will be HCl. HCl is acid, hydrochloric acid. We don't want that to interfere we don't want it to disturb ester. So we add a base here itself. So what this base does, it neutralizes the HCl that is formed. Okay, give reason, remember. Now here H plus in the presence of acid medium. What has to come and attach here? Already it has O. It wants OCOR dash. Okay, let us take this as R dash. Now it forms benzene ring OCOR dash. Ester has been formed. Now what can be the other one? So I'll tell you. Already O was there. CO and R dash. CO and R dash has formed what? The ester here. Ester has been formed. Now what is remaining? You have RCOOH. What is it? RCOOH. What is RCOOH? Yeah, here since we have taken it as R dash COOH. What is it? It's carboxylic acid. Carboxylic acid. Is it clear now of what is formed? So this is one of the reaction, that is esterification, where esterification is formation of ester from which one? When phenol reacts with either carboxylic acid or acid chlorides or acidic, that is acetyl anhydride, you get these reactions. Practice it, it's really easy. Okay. Next reaction is called acetylation. Next reaction is acetylation. What can be acetylation? You know, esterification is formation of ester. What is acetylation? Acetylation is the introduction of acetyl group. Acetylation. Acetylation is the process of, it's a process of introduction of acetyl group to the aromatic ring. Aromatic ring of phenols here. Aromatic ring of phenols. This particular reaction can be asked in two ways. One, they can ask, explain acetylation of phenols. Otherwise, they will ask you, explain the preparation of aspirin. Very, very, very important. Aspirin you have heard, isn't it? In medicinal field it is used. So in a separate chapter related to chemistry in everyday life, we will learn much detail about it. Aspirin is a tablet to cure different pains. Those tablets it is aspirin. So how aspirin is prepared? By acetylation of phenols. So we will see a product of, not a product, a derivative of phenol is taken. Phenol derivative, which is called as salicylic acid. I am writing a general one to make you understand. Salicylic acid is taken. Along with that, acetic anhydride is taken, or say acetyl anhydride, we can call it as acetyl anhydride is taken. Now here what happens is, in the presence of acid medium, in the presence of some acid medium, we get aspirin. We get aspirin along with a byproduct, and the byproduct here is acetic acid. Let us write the reaction for this. Okay, I'll tell you what is the other name for aspirin also. Shall we write the reaction? See, salicylic acid is benzene ring OH, benzene ring with OH having an acid group. This is salicylic acid. Whenever you write some reaction, write the reaction, below that you write its name also. Salicylic acid is benzene ring with OH and COOH. Salicylic acid, when you say acid, remember COOH group. And since we are studying it under phenols, you have one OH group also. Remember it that way. Acetic anhydride, you know how to write, isn't it? In the previous one, we wrote it this way. We wrote it as R dash CO twice O. Now in the place of R dash, I will take acetyl group, methyl group I will take. CH3CO twice O. In the presence of acid medium, in the presence of acid medium, it forms acetyl salicylic acid. That is the name for aspirin. See here, COOH remains same. Where the change takes place is here in this place, O, CO, CH3 comes and attaches. So it becomes O, COCH3, and this part is acetyl part. So what is the name? It is called as acetyl salicylic acid. Acetyl salicylic acid. Now, along with that, the byproduct formed is the byproduct. You can see here, which is the byproduct I said? It is acetic acid. What is the formula for acetic acid? One more, you have CH3CO. One more O you have, plus one H you have. Are you getting it? CH3CO remaining, one more O, plus, sorry, not from here, it's from here, H. So the byproduct is CH3COOH, which is acetic acid. Acetic acid. Hope it is clear now. And this acetyl salicylic acid is also called as aspirin. So they can either ask you, explain the preparation of aspirin from phenols. Otherwise, explain the acetylation of phenols. So what is acetylation? Acetylation is the process of introduction of acetyl group to the aromatic ring of phenols. That is called acetylation of phenols. Now here we have taken a derivative of phenols, that is salicylic acid, and when salicylic acid is treated with acetic anhydride or say acetyl anhydride in the presence of acid, any acid medium. In the presence of acid medium, we get acetyl salicylic acid, and acetic acid is formed as the byproduct here. Please note it, it's very important. Practice the reaction, it's really very easy. Okay, here you can remember acid means COOH, since we are studying from phenols, OH. Acetic anhydride, you know, anhydride means one oxygen will be out extra. It's like this, okay? I'll write it again. CH3CO, CH3CO, which is bonded by one oxygen. So here you can see this CH3CO has come here. CH3CO has come here. Remember, for oxygen, this CO will be bonded. Okay, not CH3 will be bonded. So this CH3CO has come here. Remaining is CH3COO, which is remaining, will take up the H that has come out to form acetic acid. Yes, we'll move on to the next reaction now. So these reactions were where you can see breakage of, in these reactions you can see breakage of OH. So we say cleavage of OH bonds. So when you study about alcohols, you see that we observe the reactions having cleavage of carbon-oxygen bond. Cleavage of carbon-oxygen bond you can observe more in alcohols. Alcohols is ROH, where this is carbon part, isn't it? If it is CH3, this way. There you can see the breaking of carbon-oxygen bond. But in phenols, you do not find a reaction much where there is carbon-oxygen bond cleavage. There is one reaction where phenols, benzene ring with OH, reacts with zinc dust. Phenol reacts with zinc dust. Okay, it will be slightly heated at some temperature. Then what happens, you know, here the cleavage of carbon-oxygen bond, which is carbon here, this is OH bond, this is carbon here. The cleavage of carbon-oxygen bond takes place and it forms benzene. Benzene as the main product. See, this way. Zinc dust. So here the breakage takes place here. So this Zn takes place, this oxygen forms ZNO, whereas this hydrogen gets attached in this place, it becomes benzene. Very easy. You have studied this reaction, yes. You have studied it maybe in hydrocarbon unit. So phenols plus zinc When phenols react with zinc dust, you get benzene along with the formation of zinc oxide. This is the only reaction of phenol where you can see the cleavage of carbon-oxygen bond. In all the other reactions, you can see the cleavage of O and H bonding. Oxygen and hydrogen bonding cleavage you can see. But in this, you can see the cleavage of carbon and oxygen. Okay, moving on to next part, where it is reactions of phenols, very important again. So reactions of phenols, when we see, these reactions are shown only by phenols. You cannot expect these reactions to be shown by alcohols. You cannot expect these reactions to be shown by alcohols. See, why I am drawing this phenol often is because the OH group is responsible for the reactions that takes place. This OH group, you know, it imparts the acidic nature also. And the effect of substituents when I was speaking, if the group, that is electron withdrawing group, are present in ortho and para position, you know which is ortho, para position. This is para, ortho, meta, this is para again, meta, ortho. If the electron withdrawing groups are present in ortho and para positions, then they show more acidity. They show more reaction. Now here when we say the reactions involving phenols, reactions of phenols, these phenols, the OH group helps for electrophilic substitution reaction. Electrophilic substitution reaction. Electrophilic substitution reactions, you know why again? Because when you have seen the resonance structure, you might have observed that in the benzene ring, say in ortho position and in para positions, you have seen during the movement of electrons, you might have observed the negative charges in these places. What does that tell you? That means that these spaces are highly electronegative. They are electron rich. When you know that they are electron rich, what are electrophiles? Electrophiles are positively charged species. These positively charged species, where do they attract? They will attract any of these position, either this or this or this position, ortho and para position. So make a note that electrophilic substitution reaction takes place due to OH group present, because OH group is highly activating group, and they direct the incoming electrophiles are directed to which positions? Ortho and para positions. Ortho and para positions. So this is clear because in the resonance structure we can see that ortho and para positions are electron rich. That is why electrophiles come and attach those areas where there is more electron rich centers. That is why electrophilic substitution reactions are favored. And these electrophilic substitution reactions, we have some important reactions which we will study in the next video. Thank you.